Well, good morning. I have the task of introducing machine learning, which, to be honest with you, is kind of a jungle. There's a variety of techniques that can be used and applied to different kinds of projects. And so my talk, since it is just an overview, kind of establishes establishes the problem, which you guys probably already have experienced if you're working in research, kind of learning from data. What do you do if you have a huge data set? What do you do if you don't have very much data? What kind of model or patterns should you apply for different kinds of problems? This talk is kind of more of a general overview, and hopefully the talks that follow this one will go into greater detail into neural networks or deep learning, if that might be of interest to you. So machine learning is quite a wide field. It actually was formerly known as statistical learning, so machine learning is kind of a newer term. If you do any kind of experiments, right, you know that you must complete some sort of statistical analysis to show or kind of give worth to your findings. So machine learning is just a kind of a new buzzword that's arisen recently. Prior to, actually when I started my PhD, I didn't even know what machine learning was, and I was doing neural networks. So neural networks at that time were being used for signal processing purposes, and that's really where I stepped in. I'm an electrical engineer by training, and so that's really how I dove into the field. But a lot of you are probably using it in very specific domains and want to know, okay, well, how can I use this as a tool? So as you already know,
you probably won't be able to imagine it, just, yeah.
Okay, so kind of what's the motivations for machine learning? Well, there's certain things that we have to take into consideration. The number one thing is, well, do I have a data set? Do I have a large data set? Do I not have any data at all? First of all, where can I find data? So there's this question of data mining that comes up that's kind of a partner to machine learning, because without really data, you can't do much unless you employ more complex models and make specific constraints or specific sort of ideas, right, that again require a lot of domain knowledge, a lot of mathematical kind of differential equations. Maybe you're modeling radiative transport, right? You're going to have to bring in a lot of domain expertise and constrain your problem so that you can verify, is this data worthy? Is this the kind of data that I'm looking for to explore this specific phenomena? Originally, machine learning drew a lot of inspiration from neural systems. It started off kind of in biology. How can we really model the brain? How can we create computers and models that can learn in the same manner as human beings? And then it kind of moved on from there. So data is everywhere. Nowadays, web data is really big. We have a lot of industry leaders that are working in this field, right? Like the big FANG companies. They have access to a lot of data. Yahoo, for example, has petabytes of web data. Actually, these statistics might as well be old. So Facebook has billions of active users that's growing every day, purchases that are being made. In fact, most of the machine learning techniques that we use today are derived from models that were created in the 1950s to describe, the Sears Roebuck catalog. So we really are kind of taking advantage of how hardware has improved over the years to manifest or implement a lot of what has already been done in the 1950s. Okay, so before you even get started with machine learning, how do we get started with finding data? Well, you might have a data set. When you start off, your data set is probably going to be pretty dirty. If you're dealing with any sort of problem, let's say you're mining it from repositories, from Kaggle, from satellite dumps, from sensory information, that information is going to need some kind of pre-processing, and that again is going to require some domain knowledge if you want to go about it intelligently. You could always just chuck it at a neural network, but that could be potentially very expensive. So going about, especially in the academic setting where you have limited resources available to you, is going to be very necessary. Then also, after you've mined your data, dealing with post-processing, making sense of what kind of patterns you can deduce from that data is going to help you move forward with your experiments. So far, most of the data mining tasks that have been defined have actually been driven by industry. So you'll see that Google, with the advent of search engines, Netflix, with their recommender systems, they have access to a lot of data that is proprietary to them, and they're interested in making as many profits as possible. So how can they really find human interpretable patterns to describe the information? And they employ a wide variety of techniques to do this, and also have a lot of resources available to them. Now, the one thing that you have to be careful of whenever you're using machine learning techniques is this particular risk that they often emphasize called Bonferroni's principle, which is, let's say that you come in with this intent, like, oh, I want to prove, I have a hypothesis, and my hypothesis is that X causes Y, right? If you go in with that mindset already, you could potentially be hurting yourself, because now you might introduce all sorts of biases that, unbeknownst to you, you're kind of building into your modeling. And essentially what Bonferroni's principle is if you really want to find something, you can make a fact out of anything, really, just by looking for it and finding the right data set that will support it. However, that might not be in your best interest and might give you things that are completely whack. Anyway, this is more on data mining. I kind of want to skip over and get to some introductory techniques that you could use. Now, the one thing that we suffer from in academia is learning from few examples. And this is something that I personally had to go through with my own PhD work. Was I wasn't able to find a data set that was to my liking, right? So finding a fully tagged data set to explore some phenomena might not be available to you. So how could you learn and come up with a model that's pretty decent with as few examples as possible? Because we aren't a Google, we aren't an Amazon, we aren't a Netflix. So this is a particular example that's often cited. This is work that was done in MIT, where human beings can learn with very few examples. So here we've got a grid of different images, and students were told that those boxed in red are called tufas. That might be a new strange animal, new strange biological entity that has tentacles at the bottom, some kind of a stem and a flowering part, and that can be identified as a tufa. Now, just based on the examples that are given here, we notice that we're not given a huge data set, but as human beings, we can identify a tufa. So do you spot any additional tufas in this grid? Anywhere? Okay, like obviously these are not tufas, right? But if you're looking for something that has this kind of root and stem flowering kind of thing, we can quickly identify what a tufa is. Now, it turns out for computers, And machines, this is not such an easy task. So you can see where we kind of could have potential pitfalls. Other examples of learning where you have limited resources available to you, meanings of words, phrases, and sentences, semantic computing. That's why NLP really is a huge field right now, as well as intuitive theories that you guys are probably all very close with in terms of physics, biology, chemistry. So even social structures, social sociology also has the same sort of issues. So how can we really extract features from data to solve predicted tasks? And what I've listed here are kind of the classic examples that are given in any kind of textbook of different sorts of machine learning techniques that are out there for different domains. Now, the main sorts of domains here, what you can see is that you really have three sort of classes of problems that you're going to be dealing with. The first class of problem is what is known as a supervised problem. And a supervised problem means that you have information about the item that it is that you seek to predict. So let's say that you're given a data set and it's a vector of attributes, a vector of values, let's call that vector X, and you want to make an inference or a prediction about a target function called Y. So Y in and of itself could also be given, and that's an example of supervised learning where you cover up Y or you learn from Y, you manipulate the data set, so you take chunks of it, you take a chunk as your test set, you take a chunk as your validation set, and then you take a chunk, hide it in a lockbox, and call that your safety test set, and you have all the answers available to you, but now with this subsets of points, of vectors, you make predictions and you build a model and test that model. The other class of problems that you're going to run into is unsupervised problems. Those are problems where you don't have the solution. And that happens to be probably the most common. Then the third class of problems you're going to get is one where you don't have much data available to you at all, but your goal is to create some sort of control agent. You might be using this in autonomous driving or an autonomous vehicle. And in that case, you would be generating your data and also updating with that data. So that's actually a different sort of machine learning kind of technology, and that's used primarily in decision making and control. But anyway, when do we apply ML? When we have issues with human expertise, although you can argue even with human expertise you need it when the problem size is basically too large. So anyway, let's actually get into some machine learning. So I'll give you kind of the Reader's Digest version of my machine learning class. Hopefully you won't get too bogged down. Again, if you have issues with the, if you need help with the math, you can always, feel free to email me and I can give you more information and some papers as well. So anyway, what is machine learning? Machine learning is basically the study of algorithms that improve their performance at some task with experience. So that experience is your data set, your X instances, your attributes, your information that you have on hand. And your goal is to do a function approximation, right? It's the same thing. We've been doing machine learning since we were in grade school. Every time we have to fit a curve, we are doing machine learning. Right? We're approximating a function based on some data points that we have available to us. Now, this function could be a target function directly, right? We could use X to solve for Y directly, or we could solve for a probability distribution. So given X, what is the likelihood that Y occurs? So that's kind of the main purpose of machine learning. Now to do this, we need to have a rich set of hypotheses or a hypothesis set. So we may have a hypothesis that the phenomena that we're looking at should be linear, or maybe it's multinomial, or maybe it's completely nonlinear, right? So those are going to be assumptions that we're going to take into account. Our input is going to be training examples, here X and Y. In the case of the supervised learning or semi-supervised, for unsupervised, you won't have Y available to you. And the target is to find the best set, the best hypotheses that can approximate that particular function. Some theoretical considerations that you can go into when you're learning machine learning in the beginning is this discussion of, is learning even feasible? The data set that I have doesn't represent reality, but is a sample taken from reality. So is that sample indicative of reality? Error versus noise, training and testing, situations that turn up according to that. Is my model generalizable? Can I use it to generalize something different, or apply it to something different? You can have a discussion about bias, variance, trade-off, overfitting, and then employ various methods of validation, cross-validation to alleviate certain things, but I'm not going to go into that. Some kind of simple models that I'm going to throw out there. Decision trees are probably the easiest to get started with, and they happen to be very robust. So at a lot of machine learning hackathons, data fests, you'll see students who don't have any particular domain knowledge at all just hook up a decision tree sort of if then else statement sort of machine learner, and it works pretty decently. We have a discussion about Bayes, since we can always take function approximation and look at it in terms of a probability distribution. We can look at the sort of Bayesian equation, and then what sort of independence assumptions can I make? The assumptions that I choose to make can change where I take my Bayes rule. I can take my Bayes rule and employ a naive Bayes learner. I could take that naive Bayes learner and then approximate that using logistic regression. I could employ a graphical model where my independencies are based on certain assumptions that I make with respect to the system. And also, what's the nature of the data I'm dealing with? Is it fully observable? Is it partially observable? Or is it unobservable in the case of an unsupervised learner? All of those are going to change the sort of techniques that I'm going to use in my learning approach. So a decision tree, what is a decision tree? We all learn decision trees when we take a programming class. It's an if-then-else statement. That's essentially all that it is. If I have this, then I have this. Now, we can take this further and say, okay, I can now construct a tree from this. I could write a sequence of if-then-else statements and create what is known in artificial intelligence as a reflex agent. And I make certain assumptions when I go ahead and I do something like this. So the assumptions that I make here is that each data set, so here I might have a data set that indicates, okay, whether or not somebody's a homeowner, what their marital status is, their income, and whether or not they defaulted on their loan. This might be a learner that I want to construct to help me make decisions as a bank on whether or not I should approve somebody's loan. Now, already there's probably going to be built-in biases to this that you have to take into account as a scientist, but just at face value, what I can do is I can say, okay, I'm going to look at each of these columns and I'm going to say, okay, count how many people are homeowners versus those that are not, And of those that are homeowners, how many people defaulted or didn't default, right? So now I can construct a tree, and the best tree is going to be the tree that gives me more information. Now, what does that mean? That means that if I start off with a sample, and let's say that I've got, 13 people that defaulted and 7 people that didn't default, I would like to come up with a decision tree where the majority of the people that defaulted are at one leaf node, and the majority of the people that didn't default are in another leaf node. So if I can somehow kind of discriminate the information as much as possible, then I have a good learner. Now I can take this further, and instead of having a tree that's quite large in height, I can create stumps of trees. I could create what is known as a forest. Now, in a forest situation, I have just one learning stump or one if-else statement, and I essentially create a forest of these if-else statements, and I give each stump a voting right. And so maybe the first stump says, okay, I think this person is going to default based on their marital status. Then maybe another stump tells me, no, based on their income, I think this is going to be the case, right? Then you just take the sum total of all those votes, and you see what the majority is, and that could give you information as to whether or not you might predict a default. So decision trees, they go well with random forests, and then you can also employ ensemble methods that include bits of linear regression at the leaf nodes. Another thing to take into consideration, and I know for some of you, this is probably like either too simple probability or maybe it's a little bit too much. There is this principle of entropy. So my goal is to decrease the noisiness of my data, right? So if I start off with a certain amount of people that defaulted on their loan and a certain amount that didn't, I would like to make sure that by the end of my leaf nodes, by the time I get to my leaf nodes, that I have now gained more information or I've decreased the entropy. If I increase the entropy, then I have a problem. I'm no better off as I was before. So there's a lot of things that you can take into consideration, but this is the main method that we use to decide whether or not a particular decision tree is a good decision tree over another. Now, there are certain limitations to decision tree learning. One glaring sort of situation that you have is, what if I'm missing information? What if I have a row or I'm missing a column that could potentially influence whether or not somebody's defaulted on a loan? Like, I took into account marital status and whether or not they own a home, but what about if they own a car and how much debt they owe on that car, or if they have student loans? Like, those are things that I didn't take into consideration. Or maybe I have a data set where nobody has ever been a homeowner. Well, what happens if I get a new piece of information about somebody who is a homeowner? Well, now that probability value that I set for that is extremely low. It's 0. So now it's like my whole model is bogus. Like, for some reason, I don't take into account people who are homeowners or car owners or whatever. So that's one of the most glaring limitations of decision tree learning. We can improve that by using a priori probability distributions, by using what is known as a map estimate, where you say, okay, I don't have this particular example. I'm just going to assign it a probability value that's really low, but I'm not going to set it to 0. The other thing that is really kind of not so good with decision tree learning is whenever you're dealing with a tree, when you're traversing that tree, that can be quite expensive. So if you've got a very large tree, that's not something that's good in terms of your compute time. So you want to decrease the complexity of your model. So that's a case where you can prune your tree, or you could just use it a forest, a random forest, where you limit the size of your trees. A lot of the methods here use basic probability. You really don't need anything beyond basic understanding of probability theory. If you get into reinforcement learning, you would have to know a little bit more about Markov chains and how Markov chains work, but that really is just another special case of Bayes. So it's not anything really beyond basic probability. So this takes us to Bayes' rule. So Bayes' rule, the great thing about Bayes' rule is that we can completely characterize any phenomena if we know the joint distribution, right? Wouldn't it be fantastic if we knew the joint distribution of somebody's marital status and whether they previously defaulted on a loan and what their salary is? If we knew all that information and whether or not they got the loan from a previous bank, then we'd have all the information we need. And if we have all the information we need, our model is perfect, right? In reality, it's not like that. So what do we have to do? We have to hack the situation a little bit. We can take advantage of Bayes' rule and say, okay, I can't really find the joint probability distribution readily. So what I'm going to do is I'm going to manipulate the joint distribution using Bayes' rule. And now I'm going to say, okay, I have some information. I have all my x's, right? So conditioned on my x's, what is the likelihood that y occurred, right? And then I can kind of hack my joint distribution and write that in terms of, okay, well, if I know y, what would the x's be? Can I maximize that instead? So you can take advantage of Bayes' rule. And then all the stuff that comes with probability distributions, you've just bought yourself by taking this assumption, right? So you can do things like calculate the maximum likelihood estimate. So what's the thing that gives me the maximal probability? Okay, that model is probably going to be the best fit model. If I don't have information about y, if I'm in a semi-supervised learning sort of situation, then I can use expectation maximization. So now I can buy a variety of techniques from probability just based on the fact that I need the joint distribution. You can build Bayes classifiers. We already know Bayes' rules, so this is really kind of fits in well. Now, the other sort of situation that happens is, okay, so Bayes' rule gives me the joint distribution. I can make some independence kind of arguments for a particular model to kind of reduce my state space to make my problem a little bit more tractable. So what are the kinds of independence assumptions that I could make? Well, the simplest independence assumption that you can make is the naive assumption. And it's actually kind of really bad. But that's how they started with spam filters. So let's say I get a bunch of emails and I want to know what email is spam. I want to tag that as spam versus an email that's not spam. So I might be looking for several keywords like Viagra. Okay, that's probably spam. Or my mom makes $38 an hour. Or Garcinia kombucha or whatever, right? So I might assign a certain weight to that word, and I might just look at 4 specific words and make them conditionally independent of one another. So that doesn't take into account sentence structure whatsoever. You're just looking for particular words, like a bag of words. Do I have this particular word? And so now what you could do is you could make the assumption that each word is independent of one another, and you can then just multiply out, take the product of all the probability distributions and make that joint distribution a little bit easier to solve for. And this is more on naive Bayes. So here I've got my Bayes rule, and I'm just making a conditional independence assumption here. Again, not very good, but good enough for a spam filter from the early, the late 90s. And then we already talked about maximum a priori estimate. This is a case where you kind of hallucinate to yourself examples that don't occur in your data set so that you don't accidentally zero them out inadvertently by saying, oh, I didn't see anywhere in the data set whether or not somebody actually was married. So because of that, anyone who is married should get defaulted because that's weird. So you can take that into consideration. This kind of takes us into, so you could go from the naive Bayes argument, and from there you can go into a logistic regression argument. In the naive Bayes case, what I do is I manipulate using Bayes rule, the joint distribution, but in the logistic regression case, I solve for P of y given x directly. So I skip the whole using Bayes rule and go directly for the y, directly for my target function. So that's where the two differ. You could argue that logistic regression, because I can derive it using the same assumptions from naive Bayes, that it's similar, but it isn't. So just be aware of that. And then there's this whole situation, what if I have discrete variables versus continuous variables? If you have something continuous, you're going to use a Gaussian. If you have something that is discrete, you are going to, you can use something binomial or multinomial in that case. Okay. So that, in a nutshell, is an example of generative versus discriminative classifiers. So generative here is the naive Bayes case versus the discriminative classifier, which is the logistic regression case. And sometimes solving for logistic regression is not so easy, so that's where you hear about using different techniques like gradient descent to automate the process using an iterative method. And again, I'm just kind of throwing it out there. So here's more information on regression. Now notice that when you are employing a lot of techniques, you have to be sure that the phenomena that you're modeling works well, that the constraints of that phenomena are going to work well. So if you are dealing with, let's say, an offshoot of logistic regression, you want to go continuous time, you do linear regression, that's actually quite constraining, right? Because now you're assuming that your phenomena is always going to be linear. So you're going to create a learner based on that constraint. So you have to really juggle that information and really understand the problem well before you dive into any kind of machine learning technique, because you don't want to give bogus results, and you also don't want to waste time. Actually, lastly, I don't actually have this here. So we had this discussion where you have the data set and you have Y fully available to you. Then we have the discussion, okay, well, I might have everything fully available to me, but I might not have enough data points for a specific phenomena, because maybe the amount of married people in my loan information data set was very few, or maybe in the subset that I chose for my testing set, I didn't have any married people. And so as a consequence of that, I was forced to use the MAP estimate instead of the maximum likelihood estimate, right? And then the other case that we had, right, we went from that conversation to, okay, now I want to make independence assumptions because solving for the joint distribution is kind of painful. It's not very nice. So I'm going to make some independence assumptions. You can take that further and say, okay, instead of arguing that everything's independent of everything else and having a very naive Bayes approach, what if I have a more domain-specific approach? What if I take the intuition that I learned from differential equations, from my textbooks, from my background knowledge, and created a model, a graphical model, and that's really where graphical models stem from, that relates some parental nodes to children nodes. So I have something that's cause and effect. So now I can make other independence assumptions. Okay, take that even further. Let's say that now I have made this graphical model, and I only have some information available to me with respect to my target, right? So there is this situation where, okay, so now what do I do? Maybe some of the data set is wrong. Maybe the sensors that I was using to measure the cloud cover didn't turn on for the specific month, but I really need that information for my climate change model. What do I do in that case? Do I just throw out that data? No, you could try using something else, right? You could try to employ classification methods, unsupervised methods. And for that, what you would do is you would say, okay, I am going to come up with several models, and I'm going to find the best fit model or the best class for this phenomena based on that model. And so now I still can save the day. My experiment didn't go to hell. So those are different approaches that you can take. What you're going to learn later today with the introduction of neural networks and deep learning techniques is that you could just say, okay, I don't have any domain knowledge, or actually you could employ domain knowledge into it as well. But let's say I just take my data set and I have a learner that's going to learn everything for me. It's going to take advantage of principles from signal processing that I can approximate any function as the linear combination of basis functions, weighted linear combination of basis functions. And then the neural net is going to spit out a solution, and I have a function ready for me. So there's different sorts of situations. Now, to that, you could still apply your domain knowledge and say, well, I'm going to come up with a cost function. I'm going to constrain that problem so that I get something that's ideal. So there's a lot of different techniques that you can employ. And those techniques really are informed by what it is that you'd like to solve for and what your situation is. But hopefully with this introduction, I threw out some models for you to kind of get started with, to play with in the beginning as a toy problem, so that you could proceed kind of with more information as to what your next step would be. So any questions?
I have a question that was kind of triggered my curiosity from yesterday's talk that Shane and Case did, that the decision tree approach, one of the benefits is explainability. Am I correct?
Yeah, so decision trees have, they're actually really great for explainability because they're if then else statements. So if you use a decision tree to decide whether or not someone gets a loan approved, if that, like, let's say a customer doesn't get their loan approved and then they come back to the bank and they say, well, why didn't my loan get approved? You could tell them exactly why. Like, oh, from our records, you have a history of defaulting on loans from other properties. You also don't have a stable salary. Your debt to income ratio is XYZ. You can explain all that information because each junction of your decision tree, each node of your decision tree is a rule. It's some kind of threshold value in terms of salary, or it could be a test to see whether or not, it could be a Boolean test. It's some kind of if-then-else statement, so you can explain it quite readily. Now, if you come up with a function that you approximate using neural networks, and you've got a very deep neural network, that neural network is going to propagate the weights, redistribute weights, and now the decision is based on some factors that you can't really explain. You might explain, the first layer quite readily, but then let's say you go deeper in, like the fourth neural network layer, explainability is really difficult. And that's not a good thing if you're making decisions that are in kind of a legal realm, because you can always have somebody come back to you and say, hey, this is a case of discrimination. I was discriminated against based on this. Why didn't I get the loan, but someone else got the loan? So explainability is really important in those kind of legal applications that have legal repercussions.
I assume science is also a mechanistic, thing, and that's also crucial for scientific applications. In fact, there is one of the projects that will be presented tomorrow is on galaxy formation, and there is a very large data set, the Galaxy Zoo Citizen data set that was done in the 90s. Some of you might have heard about that. That was done using the universal approximation theorem by having people give their opinion, just have an avalanche of opinions. And the current projects use that as a sanity check, but trying different approaches to galaxy formation, particularly decision trees. I think this project that will be presented tomorrow is using decision trees. And I'm sure a lot of you will come across situations like that where you just can't use a neural network approach because you cannot explain what you did in the end, even though you got some good results from it. In the case of Shane yesterday, I don't know if you noticed, his committee members asked him to try other approaches along the lines of neural networks, and basically to validate what he did with decision trees. And the results were not that significant. He had 52 or 3% loss of entropy versus 30%, 33%. Is there somebody here that can correct me? No? Come on, you guys are talking about that the whole talk. But you know what? It's a significant difference in that aspect. But if he had millions of data points, he could use a neural network approach. But then what? The explainability goes down the drain. You can't explain how you got there.
Well, the thing with neural networks that's really great is that you can now, because of how computing power has improved, you can run a neural net. Like when I first started my PhD, I needed a server account to run a neural net. Now with cloud computing and Keras and the open source community and all the documentation that's out there from Google, on websites like Kaggle, the MOOCs that are out there, you really have a lot of resources at your disposal. So doing a quick and dirty neural net is not out of the ordinary. It's actually good to try different machine learning models to see which one, would be a better approach if you're deciding on a good approach, or to validate what you've already kind of started, right? To kind of give you a little bit more confidence as to whether or not you're in the right direction. So I think having a wide variety of tools and techniques available to you is a good thing, because you can test them out fairly quickly.
I ask a question related to that. So, what's your perspective on how do you evaluate which one is better? Like, you know, you've got 3 different approaches that you throw at a problem, give you 3 answers that are similar but a little bit different. Then what do you do? Like, is there some, is there a methodology that people think about? Which one is the right tool?
So my approach always starts out with, do I have a data set? How large is my data set? Is it sparse? Is there information that's missing? That's gonna kind of give me an idea of, okay, can I use a neural net in this situation? For my thesis, I couldn't use a neural net. I didn't have a data set. I didn't have a data set that I needed for this specific phenomena that I was looking for. I was looking at human behavior in a house with as minimal sensory information as possible, with just the consumption load profile. Like, can I interpret what a human being is doing inside without wiring them up with cameras and all that stuff? So it turns out I couldn't find a data set that was labeled and as kind of in-depth enough. So, okay, so that kills my whole hopes of trying to use a neural network. Okay, so what can I do instead? Well, in math, what you could do is you could take an unsupervised learning sort of approach and say, okay, I am going to start taking data on myself, and I'm going to cook up several models, and I'm going to say, okay, model 1, what am I doing in model 1? And you kind of build up these models, and then you use that expectation maximization approach in an unsupervised way, and you decide, okay, of these models that I've created, and it does seem kind of hokey because you're like, well, I'm gonna, model myself. I'm going to now create a probability density based off of that, and then I'm going to run a simulation, and then I'm going to have some data and see how well it fits, or maybe apply it to another data set and see if that fits and makes sense. So you can kind of redeem yourself in a way, but you're still limited by your own perspective. Lucky for me, I was using the models in a control agent sort of situation. So I was using it in a reinforcement learning environment where it's okay to not have enough data because your agent is going to learn while it's in use. So it's going to tune the parameters of your probability density function. In my case, of my transition matrix of my Markov chain, it's going to essentially tune them. So over time, it does improve. So it doesn't really matter if what I started off with is total crap, kind of a thing. But so what I tend to do is I try to go for the easier methods first. So I also help with my students. I teach a machine learning class, and my students go to a hackathon called Data Fest, where they're given a data set that they don't even know what it is or what it's going to be on or what it's going to be like. So I just give them some tools, and the tools are usually hit it with a decision tree. If the decision tree doesn't work out and it's too deep and not useful and it takes too much compute power, turn it into a random forest, make it a forest of stumps of just one if-else statements, and then use ensemble methods on that, like AdaBoost, XGBoost. Those are packages that you can use, and see what kind of values you get there. And they usually tend to do pretty well. Linear regression always never does well enough because it's just too simple. It's way simplistic. Graphical models are good if you have some domain expertise. So let's say you go in and you know about a phenomena really well because you have all that training. You can go at it not so blind, then you can kind of tune the independence assumptions that you make in your using Bayes' rule. I think that approach lends itself well, especially for graduate students. That's actually why I went kind of the Markov way, because I was making specific independence assumptions. So I think that that helps a lot too. Neural networks is kind of you can get caught up in it because it's so magical. I don't know how to explain it. So when I started off, I would just throw everything into a neural net, because you just get a package, you run the neural net on it, or you code the neural net yourself, you run it, it runs for a few days, and it spits out an equation. And it just seems amazing. But then what? So it was really difficult to write a paper on that, like trying to explain that neural network. So it's great if you want quick and dirty results, but it's kind of difficult to justify and then write several sections on in an academic paper. So I kind of just gave up on that one.
I ran a neural net, this is what it told me.
This is what it told me.
You got nothing else.
Yes. So yeah, so using any of these other methods is a little bit better. Doing both is really good, because then you can say, oh, you know, this is kind of my reasoning, and the neural net corroborates that, and here's, you know, an extra little number in my results section. So,
But, I mean, just to attempt an answer to
yeah.
using neural networks, you need to be careful with having a cross-validation set, a test set, and if you have enough data, that can, you know, validate your results. And it's like she said, magical, right?
That goes for any model. Any model you do, if you have data, what you're dealing with is a sample of reality. So you need to subdivide that sample. So you should do cross-validation all the time, because you could be guilty of data snooping if you use the whole data set. Then you're just biasing your results. Your result is junk. So to keep yourself sane and your experiments sane, you should always cross-validate, irrespective of whether you use neural networks or you use decision trees or you use some other sort of method like Gaussian mixture models or whatever. So always do that. That's not just for neural nets. Always cross-validate. Yeah. But I guess I didn't really answer your question, but
Well, it sounds like there's no clear answer.
there's no clear answer. You just kind of, you just kind of have to you have to look at what data you have available to you, what is the problem that you want to solve, will your domain knowledge help? Most likely it will.
Just a very simple nomenclature question.
No, okay.
What's the difference between a decision tree
So a regular decision tree can be it can be as deep as you want it to be. You don't constrain the height of the tree. You're dealing with one tree. Potentially, you could have one tree that describes the entire phenomena. In a boosted tree, whenever you're doing boosting, you're employing what is known as ensemble methods. And what ensemble methods do is they take pieces of other modeling techniques and apply it to the tree. So in the example of the loan, whether or not somebody defaulted on a loan, or whether or not you should accept a candidate's application. One of the attributes we were looking at, the data attributes, was the salary, for example. Salary is a continuous variable. So at each of the leaf nodes, right, instead of having a yes or no kind of a Boolean answer for that, what you would have is maybe a linear regression or a multinomial regression that you would fit. So boosted trees and forests, they're known as ensemble methods because they apply other techniques to the leaf nodes, as well as generate multiple trees that now have voting rights. You could have them each have a uniform value for the vote, where they all have equal votes, or you could give some trees more weights than others than you'd have a probability distribution across the individual trees of the forest. So there's different boosting techniques that are out there, and that would take a little bit of time, but it's a good question.
All right. Thank you. That was very nice.